Welcome to this lecture about heat pumps in cooling mode. We call them chillers or cooling machines. And this is the first of the cooling systems we are going to study. The basic principle was explained in an earlier lecture. We have already made an energy balance on the chiller. Electricity in plus heat input from evaporator should be equal to the heat delivered at the condenser plus some heat lost in the pipes and the casing. As we are in cooling mode, we are interested by the heat removed at the evaporator side, which is in fact the cold produced, for instance, inside your fridge or in a room with air conditioning. We cannot define here any efficiency in the strict sense of it, as the heat output this time is not of interest, but we can define a kind of coefficient of performance for this cooling mode, the so-called EER. It is defined as being the heat input to the evaporator, which is in fact the quantity of heat taken away from the room or the fridge, divided by the electricity needed by the compressor. The EER can be lower than 1, but in modern cooling machines it will be higher. This time, the Carnot EER, which is the maximum EER the chiller can achieve, is determined by the ratio of the cold heat source temperature Tc by the difference between Th and Tc. Let's take the example of a chiller cooling a room to a temperature of 24 degrees Celsius. This is the heat source of the chiller and therefore the temperature of the heat input Tc. But where to reject the heat? Generally, the condenser heat will be rejected to the outdoor air. Imagine it is warm and the outdoor air has a temperature of 40 degrees Celsius. The Carnot EER would be 273 plus 24 equals 297 divided by 40 minus 24, which is 18.6. Here too, perfect heat exchangers do not exist, and there must be a temperature difference between the indoor air and the refrigerant in the evaporator, and also a temperature difference between the outdoor air and the refrigerant in the condenser. In cheap air chillers, large temperature differences between the air and the refrigerant can be observed. If the temperature difference is 7 degrees, Tc becomes 13 because the refrigerant must be cooler than the air to be able to take its heat up, while Th becomes 47 because the refrigerant has to be warmer than the outdoor air to release its heat. This way, the EER decreases to 8.4. Producers give the EER of their chillers as being the Carnot EER times the Carnot efficiency, which here too accounts for non-ideal heat exchange in the evaporator and the condenser, and for all losses in the compressor and in pipes, valves and casing. Just like for heat pumps, producers of chillers must specify the EER for different outdoor and load conditions and provide a formula to calculate the seasonal EER, the SEER, depending on the frequency of occurrence of partial load for a certain climate. Contrary to heat pumps, there is not much choice in the heat source of the chiller. The heat source must be either the room air to be cooled or a cooled water system connected to floors or ceilings or connected to an air handling unit to indirectly cool incoming air. Imagine now a day with an outdoor temperature of 35 degrees Celsius. Th is therefore 35. Let's assume a Carnot efficiency of 0.4. We use first a chiller to directly cool the room air to 18 degrees, like is done often in the US. The EER, using the formula above, will be 6.8. If the room air is now cooled to 24 degrees, like is done in Europe, it leads to a EER of 10.8. We gained 59% in efficiency, which means 59% less energy is used. And additionally, it is more comfortable because 24 degrees inside is by hot weather much finer than 18. Let's now look at a central water cooling system for an air handling unit. You see below in the picture the cooled water circulating from the evaporator to the air handling unit. In the air handling unit, the warm air flows along the cool water and is cooled this way. In many countries, there is a need and a necessity for dehumidification. To dehumidify the air, the water vapor contained in the air must be condensed, and for this, real cold water is needed at around 9 degrees. This leads to an EER of 4.3, much lower than the precedent ones. In many other climates, there is not a real need for dehumidification, and centrally cooled air at 14 degrees can be provided and mixed with the room air, leading to a nice indoor temperature. This would also be the temperature needed in a floor or ceiling cooling system, by the way. It would give an EER of 5.5, 28% better than with the temperature of 9 degrees. So, to get the maximum efficiency from a cooling machine, high temperature cooling should be preferred whenever possible. We have looked extensively at the heat source's temperature. But what about the heat sink and the temperature TH at which the heat is delivered? In the formula for the EER, we see that it has an impact. TH should be chosen as low as possible in order to increase the EER as much as possible. Most chillers reject their condenser heat to the outdoor air. Let's look at the temperature graphic on the left and look at what happens in hot summer. The air temperature is in general much higher than the temperature of the sea or lakes, while the shallow ground has the lowest temperature. Let's look at the effect of this heat delivery temperature on the EER by taking the example of central water cooling for floor cooling. TC is 14 degrees. We already calculated the EER when rejecting the heat to the outdoor air at 35 degrees. It was 5.5. If we would now connect the condenser to a pond, lake or sea water, we could reject the heat at 20 degrees, which would lead to an EER of almost 19.1, 3.5 times higher than when using the outdoor air. Just like for heat pumps, care has to be taken that the rejection temperature is below a certain limit in order to limit the burden to the flora and fauna in water. And last but not least, if we could reject the heat to the ground, which has almost the same temperature as the cooled central water, the EER would become huge, 115. This is, of course, much more expensive than using a simple air heat exchanger, but it is technically possible and is sometimes done in combination with aquifer thermal storage. You see here some examples of chiller units. On the left, the evaporators of air chillers, above in domestic application, below for an office building. In the middle, above, you see a complete roof unit, and below, a big chiller in New York used for district cooling. And on the right, you see a picture with ground source chiller. The chiller is on the left of the picture and can also work as a heat pump. In the middle of the picture, you see a big ground heat exchanger. In this heat exchanger, groundwater from an aquifer at 70 meters depth is pumped and takes over the heat rejected by the condenser of the chiller. The evaporator side of the chiller produces cold water for the air handling unit and for the floor cooling. This last picture was about a reversible chiller or reversible heat pump. We have looked separately at heat pumps and chillers, but as the principle is the same, it may be very convenient to use one device for both heating and cooling. This can be done seasonally. For instance, in the case of floor heating and cooling, the pipes to and from the floor would be connected to the condenser in winter and to the evaporator in summer. In the slide, you see in solid lines the heat pump mode, delivering heat to the floor heating. In dotted line, you see the cooling mode. This time, the floor is connected to the evaporator and cooled down, while the heat from the condenser is rejected to the ground. This way, less space is needed for the equipment, and the costs may be expected to be lower than if both a heat pump and a cooling machine must be bought. In office buildings, in cold and moderate climates, it happens often that heating is needed for a part of the building, while another part is in need of cooling. Think, for instance, of the server room. meeting rooms or the company's restaurant. In this case, it is very convenient to use the condenser side to heat and simultaneously the evaporator side to cool. Of course, some attention has to be paid to the design temperatures. They must fit with the aims. The reversible heat pumps you saw in the last slide is able to do both, by the way. We have handled the compression cooling machine, but what about the absorption chiller with its thermal compressor? Well, from the energy balance we can deduct here too the EER, which is useful cooling divided by electricity input at the pump, if we are not accounting for the input from the waste heat. When the desorber is not using waste heat, but heat generated for this purpose, we must account for it. Here too, the EER is the Carnot EER multiplied by the efficiency of the thermal compressor and by the Carnot efficiency. The efficiency of the thermal compressor can be shown to be the temperature of the heat input to the desorber minus the temperature in the absorber divided by T-abs. As for the Carnot efficiency of absorption chillers, it is defined by the high condenser temperature divided by the temperature difference between condenser and absorber. In general, the efficiency of absorption chillers is much lower than the one of compression chillers, except if waste heat can be used to drive the thermal compressor. Let's look now at the primary energy and CO2 emissions. Imagine we have an electrical chiller with a seasonal EER of 2.5. If the cooling demand is 3000 kWh, we need 3000 divided by 2.5 is 1200 kWh electricity to power the chiller. Let's consider that the electricity is produced in a gas power plant with efficiency 0.4. So the annual primary energy is then 3000 kWh, 1200 divided by 0.4. So the true efficiency of this chiller is not 2.5, but 0.4 times 2.5, which is 1. And how much gas is that? Well, the higher heating value of North Sea gas is 9.8 kWh. Dividing the primary energy by this heating value gives the quantity of gas needed, which is 306 cubic meter. And the CO2 equivalent emissions are 600 kg CO2. And of course, if the electricity was produced by renewables, this would be 0. In this lecture, you have discovered how the EER of chillers is determined by the temperature levels of the heat source and the heatsink. To obtain a high efficiency, it is very important to limit the temperature difference between the sink and the source. This is why low stable heatsink temperatures are preferred. At constant source temperature, a ground source chiller will have a higher EER than a water one, than an air one. Ground source chillers are unfortunately not very common, and the vast majority of commercial chillers uses outdoor air as heatsink. High temperature heat sources are essential as well for a high efficiency, and therefore high temperature cooling systems are preferred, like floor cooling or direct air cooling. If the air must be dehumidified, a low source temperature is needed and the EER of the chiller will drop enormously. When making estimations of primary energy use over a year, it is recommended to work with the seasonal EER, and finally, it is very well possible to engineer reversible heat pumps and chillers that can switch easily from the cooling mode to the heating mode and vice versa. Thank you for your attention, and I hope you have noticed the similarities between this lecture and the one on heat pumps. It was on purpose.